In this lecture, we'll discuss linear search. This linear search is the most basic and simplest of all searching techniques. It is also called sequential search. In this technique, we start from the beginning of the list and sequentially check each element of the list one by one. We'll stop when either we find the search value or when we reach the end of the list. If we reach the end of the list and still the search value is not found, it means that the search value is not present in the list. So in this case, we call this an unsuccessful search. And if we find the search value, then we call it a successful search. Now suppose we have this array and we have to search this value 46 in this array. We'll start from first element and we'll compare the search value with each element of the array one by one. We find this value 46 at index 5. So our search is successful. Now suppose we have to find this value 53. We compare with all the elements of the array one by one and we reach the end of the array. But this value was not found. This means that this value 53 is not present in the array and our search is unsuccessful. The implementation of this linear search is very simple. So now let's see the program for this. This is the method main. In this array, we'll perform linear search. Here we are entering the number of elements of the array and here we are entering the elements. And here we are entering the value that has to be searched. Now we are calling this method search with these three arguments. This A is the array in which we'll search, N is the number of elements, and this is the value to be searched. This method will return -1 if the search value is not present in the array. Otherwise, it will return the index at which the search value is present. Now let's see this method search. In this for loop, we are scanning the array starting from the first element. If the search value is found, then we return the index where it is found. Now if the control reaches here, it means that we have checked the whole array and the search value was not found. So in this case, we return -1, indicating unsuccessful search. Now let's run this program. Now let's see the performance of this linear search algorithm. Best case for linear search is when the search value is present at the first position only. And in this case, only one comparison is required. So this is order of 1. Worst case is when the search value is not present in the list. And in this case, we have to loop through the entire list. So in the worst case scenario, there are n comparisons required to search for an item in a list of n elements. So the worst case performance of linear search is order of n. Now let's see the average case performance. To search an element that is present at ith position, I comparisons are required. The average number of comparisons needed in a successful search, assuming that the probability of searching of all elements is same, will be this. And this is order of n. So in both average case and worst case, the runtime complexity of linear search is order of n. Now this linear search can be used for linked lists also, because in this algorithm, random access to elements is not required. We have already discussed linear search for linked lists in the linked list section. We'll study another algorithm, binary search, which is more efficient than this linear search, but it can't be used on linked lists as it requires random access to elements. Now in the next lecture, we'll see two variations of this linear search. In this lecture, we'll see these two variations of linear search that can improve the speed of searching. First, let's see this linear search using a sentinel. We can make the basic linear search algorithm a little faster if we use a search value as the sentinel value. Let's see how. Now, in each loop iteration of linear search, we are doing two comparisons. This comparison, I is less than n, and this comparison. Now, this comparison, I is less than n, we are doing so that we don't cross the array boundary. If the search value is not present in the array, and if we don't have this condition, then we'll go past the array boundary. Now, we can eliminate this comparison I is less than n if we place the search value at the end of the list. So if we have n elements, then we can temporarily place the search value at index n of the array. For example, in this array, we have to search for this value in these 11 elements. So we have placed this search value 34 at index 11. Now if we have to search for value 52, then we'll place this value 52 at index 11. So this sentinel value will terminate the search when the search value is not present in the array. Now we'll never go past the array because the search value will always be found and this condition will definitely become true. This is called linear search with sentinel and it reduces one comparison in each iteration of the loop. Now let's see the program for this. This method main will remain same as in our basic linear search. Now in this method search, we are placing the search value at nth index of the array. In our basic linear search algorithm, we had a for loop. Here we have replaced it with a simple while loop. And now we have only one comparison in each loop iteration. After this loop terminates, if I is less than n, it means we have found a real match. Search is successful and so we return the index where the search value was found. If the search value is not present in the array, then this loop will terminate because of the sentinel value present at index n. So after this loop, if I is equal to n, in that case, the search is unsuccessful and so we return -1. So in linear search with sentinel, we always find the search value and therefore we don't have to check for array boundaries. To implement this sentinel search, the array size should be at least one more than the number of elements. If the array size is equal to the number of elements, then we can take a temporary variable, store the last element in that variable, and after the search is over, we can place the last element back at its original place. Now let's see the other variation of linear search. The efficiency of linear search can be improved if the list is in sorted order. In the linear search algorithm that we have seen, we had assumed that the array is not sorted. So if the search value is not present in the array, then we have to check all the elements of the array till the end and then only we can say that the search value is not present in the array. If the array is sorted in ascending order, then as soon as we reach an element that is greater than the search value, we can say that the search value is not present in the array and we can terminate the search. We need not go till the end of the array. So the number of comparisons in the case of an unsuccessful search can be reduced if the array is sorted. Suppose we have the sorted array and we have to search for value 50 in this array. When we reach this element 52, which is greater than 50, we can terminate our search. There is no point in continuing the search beyond this element because all the elements to the right of this element are greater than the value 52 and hence they are greater than the search value 50. So there is no possibility of 50 being present beyond this element. So if the array in which we are searching is sorted, then the performance in the case of unsuccessful search is improved. Now let's see the program for this. In this method main, we are entering the elements of the array in sorted order. Rest of the method is same as in our basic linear search. Now this is the method for linear search in an ascending order array. We terminate our search as soon as we find an element that is greater than or equal to the search value. If the element is equal to the search value, the search is successful. So we return this index where the search value was found. Otherwise, the search is unsuccessful. And in that case, we return -1. So if the array is sorted, we can determine the absence of the search value more quickly. We need not traverse the entire list for it. This speed improvement that we get by using sorted array is only for an unsuccessful search. For a successful search, the performance is the same as the basic algorithm of linear search. So we have seen two variations of linear search. We can combine both these variations to perform an efficient linear search. If the array is sorted, then binary search is more efficient than linear search. We'll discuss binary search in the next lecture. In this lecture, we'll discuss binary search, which is order of log n performance. This binary search works only on sorted arrays. So the prerequisite for binary search is that the array should be sorted. Now let's see how the algorithm works. We start by comparing the search value with the middle element of the array. If the search value is equal to the middle element, we are done. The search is successful and the position of the middle element is returned. Now, if search value is not equal to the middle element, we'll use the sorted nature of the array to reduce our possible search space to half. Let's see how. We'll divide our array into two halves. The first half contains all the elements to the left of the middle element and the other half contains all the elements to the right of the middle element. Now we know that our array is sorted, so all the elements in the left half will be smaller than the middle element and all the elements in the right half will be greater than the middle element. Now if the value being searched is less than the middle element, then it must be present in the left half only because all values smaller than middle element are present in the left half. So we continue searching in left half and we eliminate the middle element and the entire right half from further consideration. Now if search value is greater than the middle element, then it must be present in the right half only because all values greater than the middle element are present in the right half. So in this case, we continue searching in right half and we eliminate the middle element and the entire left half from further consideration. So the search is continued in either the left half or the right half. And the search is performed using this same process. Now we are searching in a smaller portion of the array. We can say that we are searching in a sub-array. If we have to continue searching in left half, then we'll find the middle element of this sub-array and we'll compare the middle element with the search value. If they are not equal, we'll again divide the sub-array into two halves and the search is performed in one of those halves. Similarly, if we have to continue search in the right half, then we'll find the middle element of this subarray and we'll compare the middle element with the search value, and if they are not equal, we'll again divide this subarray into two halves and the search will be performed in one of those halves. Now this process is repeated, and in each step we split a subarray into two halves and we eliminate one half from the possible search space. And this process will stop when either we find the search value or when we get a subarray of size 0. That is a subarray which does not have any element. Now if the array contains even number of elements, there will be two candidates for middle element. In our examples and code, we'll take the first one is the middle element. Now let's understand this whole process with the help of an example. Suppose we have this array and we have to search value 46 in this array. Clearly this array is sorted, so we can perform binary search. Now this is the middle element. So we compare this search value 46 with this middle element 70. Now 46 is not equal to 70. So we have to continue searching in this left half or this right half. Now 46 is less than 70. So it has to be present in this left half. It can't be there in this right half. So we continue searching in this left half and we ignore this middle element and this entire right half. Now for this subarray, this is the middle element. This is not equal to 46. So we have to continue searching in this left half or this right half. Now 46 is greater than 32. So it has to be present in the right half only. So we continue searching in this right half and we ignore this middle element and the left half from further consideration. Now for this subarray, this is the middle element. Now when we compare this search value with this middle element, we find that they are equal. So the search is successful. Now in the next lecture, we will see how we can implement this procedure. In this lecture, we will see how to implement binary search. We'll take three variables: first, last and mid. This variable first will denote the index of the first element of the subarray in which we'll search. And this variable last will denote the index of the last element of that subarray. Initially, we'll have first equal to 0 and last equal to number of elements minus 1. As the algorithm proceeds, we'll search in smaller subarrays, so the value of first and last will keep changing. This variable mid will denote the index of the middle element of the subarray in which we'll search. We'll calculate the value of mid from the values of first and last. Now suppose this is a subarray in which we are searching. This is the middle element of this subarray. This is the left half and this is the right half. So we can see that the left half is from index first to index mid minus 1 and the right half is from index mid plus 1 to index last. So A mid is the middle element and elements from A first to A mid minus 1 form the left half, and elements from A mid plus 1 to A last form the right half. Now the value to be searched is compared with the middle element. If it is equal to the middle element, search is successful. If it is smaller than the middle element, then we have to search in the left subarray. Now for left subarray, index of first element is first only, while the index of last element is mid minus 1. So we update variable last, while variable first remains the same. Now if search value is greater than the middle element, then we have to search in the right subarray. For right subarray, index of first element is mid plus 1 and index of last element is last. So here we update variable first. Now this process is continued, and when first becomes greater than last, we get a subarray of size 0. There is no portion left in which to search, so the search is unsuccessful. Now let's understand this with the help of some examples. We have the sorted array, and suppose we have to search value 40 in this array. Index of first element is 0 and index of last element is 17. So variable first is equal to 0 and variable last is equal to 17. Now we calculate mid. It comes out to be 8. So this is the middle element. Now the search value is less than this middle element. So we have to search in this left half. We ignore this middle element and the right half. Now for this left subarray, index of first element is 0. So we will not change this variable first. Index of last element is 7, which is equal to mid minus 1. So we'll update the variable last. So now last is equal to mid minus 1, last is equal to 7. Now we have to search in this subarray. So now again we'll calculate mid. It comes out to be 3. So this is the middle element. Now this search value 40 is greater than the middle element. So we have to search in this right half, and we ignore this middle element and this left half. Now for this subarray, index of first element is equal to 4, which is equal to mid plus 1, and index of last element is 7. So we will not update this variable last, we'll update this variable first. So now first is equal to mid plus 1. So first is equal to 4. We have to search in this subarray. So again we calculate mid. It comes out to be 5. This is the middle element. We compare 40 with this middle element. 40 is less than 46. So we have to search in the left half. And so we'll ignore this middle element and the right half. And then we'll update the value of last. So now last becomes equal to 4. Again we'll calculate mid. Mid comes out to be 4. We compare this search value with this middle element. Now we have found the search value, so the search is successful. Now suppose we have to search this value 88 in this array. This is the variable first, this is the variable last. We calculate mid, comes out to be 8. So this is the middle element. We compare 88 with this middle element. 88 is greater than 70. So we have to search in this right half. And so we will ignore this middle element and the left half. And now we'll update the value of first. So now first becomes equal to 9. And now we have to search in this subarray. So again we'll calculate mid. It comes out to be 13. So this is the middle element. Now we compare this search value with this middle element. Both are equal. It means that the search value is found and the search is successful. Now suppose we have to search for this value 13. This is first, this is last. We calculate mid. It comes out to be 70. We compare 13 with 70. 13 is less than 70. So we have to search in this left half. So we'll ignore this middle element in the right half. And then we'll update the value of last. So now last is equal to 7. We have to search in this subarray. Again we'll calculate mid. It comes out to be 3. 13 is less than the middle element 32. So we have to search in the left half. And so we'll ignore this middle element and right half. And then we'll update the value of last. Now last is equal to 2. We'll calculate mid. So this is the middle element. Now when we compare this search value with the middle element, we find that they are equal. So the search value is found and the search is successful. Now we'll see an example of unsuccessful search. Suppose we have to search for this value 80 in this array. This is first, this is last. We calculate mid. Now 80 is greater than 70. So we have to search in this right half. We ignore this left half and this middle element. And we update the value of first. So now first is equal to 9. We have to search in this subarray. We calculate the value of mid. This is mid. Now 80 is less than 88. So we have to search in this left half. We'll ignore this middle element and the right half. And we'll update the value of last. So last is now equal to 12. We have to search in this subarray. So again we calculate the value of mid. Mid is equal to 10. Now 80 is greater than 79. So we have to search in the right half. So we'll ignore this left half and this middle element. And now we'll update the value of first. So first is equal to 11 now. Now we have to search in this subarray. We calculate the value of mid. Mid is equal to 11. 80 is less than 81. So we have to search in left half. So we have to ignore this middle element and right half. And we update the value of last. So now last becomes equal to 10. Now the value of first has become greater than last. It means that the search is unsuccessful. The search value is not present in the array. Now let's see the program for binary search. This is the method main. In this array A, we'll perform binary search. Here we are entering the number of elements. And here we are entering the elements of the array. The elements of the array should be entered in sorted order, since we can perform binary search only on a sorted array. Here we are entering the value that is to be searched. Now we are calling this method search with these 3 arguments. This A is the array in which we will search, N is the number of elements, and this is the value that is to be searched. Now this method will return -1 if the search value is not present in the array. Otherwise, it will return the index at which the search value is present. So now let's see this method search. We have taken 3 variables, first, last and mid. This variable first will store the index of first element of the subarray in which we will search. This variable last will store the index of the last element of the subarray in which we will search. And this mid will store the index of the middle element of the subarray. This variable first is initialized to 0 and last is initialized to n-1. We have seen that the process of searching stops when variable first becomes greater than last. So this loop continues till first is less than or equal to last. When first will become greater than last, this loop will terminate. Now here first we are calculating the value of mid. If search value is less than the middle element, then we have to search in left half. And so we update the value of last. Otherwise, if search value is greater than the middle element, we have to search in right half. And so in this case, we update the value of first. Otherwise, the search value will be equal to the middle element. And in that case, we return mid, which is the index where search value is found. Now, if the search value is not present in the array, then variable first will become greater than variable last. This loop will terminate and control will come here. And in this case, we return -1, which is not a legal array index. So a return value of -1 will indicate unsuccessful search. Now let's run this program. Value 4 is not present in the array. Value 3 present at index 1. Now let's see the recursive method for binary search. Here we have called this method search with these three arguments: array, number of elements, and search value. Now inside this method search, we have called this recursive method search. And this is the recursive method search. We have these two recursive cases, this and this. And we have these two base cases, this and this. So in this case, the search is unsuccessful. And in this case, search is successful. Here we are calculating the value of mid. Now if search value is greater than the middle element, then we have to search in the right half. So we call this method search recursively for the right half. And for the right half, the index of first element is mid plus 1 and index of last element is last only. If search value is less than the middle element, then we have to search in the left half. So we call this method search recursively for the left half. And for the left half, index of first element is first only, index of last element is mid minus 1. So this is how this recursive method works. In this lecture, we will analyze the binary search algorithm. The best case for binary search would be when search value is present in the middle of the list. So in that case, in the first comparison only, the search is successful. So we need only one comparison. Now the worst case is when the search value is not present in the array. Now let's see how many comparisons will be done in the worst case. We have seen that each time we make a comparison with the middle element, we can eliminate about half of the elements from consideration. That is, we reduce the size of the subarray to almost half. So if we start with n elements, then after one comparison, we'll have about n by 2 elements left. After 2 comparisons, we'll have about n by 4 elements left. After 3 comparisons, we'll have about n by 8 elements left. After I comparisons, we'll have about n by 2 raised to the power I elements left. Now in the last step, we'll have only one element left. Now to find the comparisons that will be done till the last step, we'll have to find the value of I when this value is 1. So we have this. Now multiplying by 2 raised to the power I on both sides, we get this. Taking log of both sides, we get this. So this is the maximum number of comparisons required in a binary search. And so binary search algorithm is order of log n. We know that logarithms grow much slower than the linear function. So binary search is more efficient than the linear search. Suppose we have a list of 10,000 elements, then we'll need at most 13 comparisons in binary search. And this is definitely much better performance than the linear search. Now, although binary search has better performance than the linear search, we have to keep in mind that it involves additional cost of sorting, which may sometimes not be worth it. It is generally preferred when the data is static, when there are very few insertions and deletions. If there are frequent insertions and deletions, then maintaining the data in sorted order involves lot of movements and it proves costly. We cannot use binary search on linked lists because it requires direct access to the middle element. And in linked lists, we don't have direct access to the elements of the list.